point P is one vertex of a regular pentagon in an Argand diagram. The center of the pentagon is the origin. And we're given that P represents the complex number 6 plus 6i. So let's put it on here. That is 6, and that is also 6, and here's the center. We're asked to then determine the complex numbers that represent the other vertices of the pentagon, giving our answers in the form r e to the I theta, so polar form. And that's a little bit of a hint in this question. It wants us to write down the complex number 6 plus 6i in polar form. We can do that. So to get the magnitude, it's just going to be 6 squared plus 6 squared square rooted. That ends up being 6 root 2. And then the argument, if I call this z, then it's actually going to be pi over 4. You can either do inverse tan of 6 over 6, inverse tan of 1, which is pi over 4, or you might be able to recognize that, look, it's the same value. So it would be a 45-degree isosceles triangle. And that means z is going to be 6 root 2 e to the pi over 4 I. Now let's think about the other ones. They're all going to have the same modulus of 6 root 2. And there's one other thing to think about. Let's just sketch out a regular pentagon. We don't know exactly what it's going to look like. But if you go from the center, then all of these angles are the same. In fact, they're 360 divided by 5, but in radians, 2 pi divided by 5. And that gives me my way in for the next, the next complex number. It's going to have the same modulus, but I just need to go another 2 pi over 5 radians to get my next point. And then again, and then again. And we're going to somehow construct this regular pentagon. So all we've got to do is add 2 pi over 4 onto, 2 pi over 5 onto pi over 4, and we'll get there. Now, when I did it, I was like, I can just say that all my answers are simply 6 root 2 e to the I pi over 4, and then I'm going to be adding on 2 pi n over 5, where n is then going to, because it's, what am I trying to find? The other vertices, n is then going to be 1, 2, 3, and 4. Of course, when it's 0, we've got the 6 plus 6i, and then I'm just going around the axis an extra 2 pi over 5 every time. I didn't seem to accept that in the mark scheme, so I am, especially that this is 5 marks. Okay, let's play a bit safer and write each one down. So we're just adding 2 pi over 5 on every time. You can put it into your calculator, and you end up getting 6 root 2 e to the 13 pi over 20i. Then the next one is 21 pi over 20i. We're actually just adding on 8 to the numerator every time. So the next one is going to be 29 pi over 20i. And then 37 pi over 20i. And these are other 4 complex numbers which make up the regular pentagon. Now this next part has nothing to do with what we've just done. We're asked to draw an Argand diagram and shade a region that satisfies these 2 loci. So let's take a look at the first one, and we'll build it up. So if we had to draw the modulus of z equals 2, that's all my complex numbers with a length of 2. And it would actually give us a circle, centered at the origin of that. That's when it's equal to. less than or equal to would then be the whole area inside. Now, when we minus 2i, just treat it as a transformation. That's how I think about it. So it's going to be a translation by 2 in the positive imaginary direction. And remember, the radius is also 2, so it's going to move up to here. And you must make sure that very bottom goes through the origin. That will be expected. And we'll just put the center on. It's going to be at 2. Okay, I'm not going to shade it yet because we've got this other one to deal with. The argument of z, okay, no translations this time. We're going to be drawing lines from the origin. Okay, and it's between pi over 4. That's 45 degrees. So just make sure you draw a line that pretty much looks like it's going like it's the bisector of that right angle here. And then it's we've also got pi over 3, which is 60 degrees. So yeah, something like that. Make sure it is going through that origin. Technically, we should put a little circle here because it can include it at that origin. And that would be when they're, well, that's, I've drawn like that equals that and that equals that, but we're looking for where it's in between the angles and we're looking for where it's inside the circle. So our region is going to be this. Shade the region R. I'll just, inside, I'll just call it R, capital R. I'll determine the exact area of R, giving your answer in simplest form. So this took me a little while. I was like thinking, it's not like a simple segment or something like here. It's not a sector. It's something in between. So we can work out that area by subtracting other areas. And actually, that's how I ended up doing it. And I will talk through that method because I thought, sure, could we do some sort of integration here? And it turns out you can, and that's how most people actually did it in the real exam. And fair play, because I personally don't think it's easy, but maybe I just need to practice my polar integration a bit more. But that's how I'm going to go through it first of all, and then I'll go through it a second way. Because the nice thing about this is it is a relatively simple curve. We've got a circle centered at 0, 2, so I can write it in Cartesian form as x squared plus y minus 2 squared equals 2 squared, or 4. And then I want to write down this in polar form to be able to integrate it because I'm integrating between these two angles. That's why we want to work in polar form. So we've got that r is equal to, sorry, not r, x is equal to r cos theta and y is equal to r sine theta. So we can sub these in and we'll get r squared cos squared theta plus r sine theta minus 2 squared equals 4. Therefore, r squared cos squared theta plus r squared sine squared theta minus 4r sine theta plus 4 is equal to 4. This I can end up factorizing, and then I get 1. The 4's cancel, and so suddenly I've got 4r sine theta equal to r squared, and therefore r is going to equal 4 sine theta. Now that I don't just look at that curve and think immediately it's 4 sine theta. So if you're somebody who does see that, then let me know how you did it more quickly, because the mark scheme just goes straight in and says, oh well, r is 4 sine theta, but maybe I just not practiced my polar formulae enough. But that is what we need. And now if I want the area, then it's going to be a half times the integral of r squared with respect to theta. And we're integrating, remember, between pi over 4 and pi over 3. And then I'm going to square this, so r squared is going to be 16 sine squared theta. And I'm going to get 8 times the integral of sine squared theta. And this is an integral that okay, it takes a bit of time, but one that you should be familiar with. We're going to use double angle formulae. I always go back to the very beginning. You might learn the expressions if you do it enough. I don't. I just do it every time. So cos 2a is going to be cos squared a minus sine squared a. Replace cos squared by 1 minus sine squared. I'm going to get 1 minus 2 sine squared a. Rearrange. Sine squared a is then going to be a half 1 minus cos 2a. So this here is going to become 4 times the integral from pi over 4 to pi over 3 of 1 minus cos 2 theta. Okay, I'll move over here. So I will then get 4, right, let's integrate. I'm going to get theta minus a half sine 2 theta evaluated between pi over 3 and pi over 4. Okay, I brought the 4 out of the whole thing. That's absolutely fine. Then I'm going to get pi over 3 minus a half sine 2 pi over 3. Then I'm minusing pi over 4, and I end up adding a half sine pi over 2. Pi over 3 minus pi over 4 becomes pi over 12. Sine 2 pi over 3 is actually the same as sine of pi over 3, which is root 3 over 2. So I'm going to get minus root 3 over 4, whilst sine pi over 2 is 1. And then finally, we get pi over 3 minus root 3 plus 2. And that is our exact form. We can't simplify it anymore. That worked really well. All right, method 2. There's different ways to cut the circle up, I think, but I'm going to show you how I did it. Okay, I want to find this purple area, but this time no polar form, just creating areas that I know how to calculate. So one thing we can do is, and I haven't drawn it particularly accurately, but this should be a quarter of a circle. See, that point there should be in line with the 2. And so that will allow me to work out this segment pretty quickly. I'm going to call it R1 because it's going to be a quarter of a circle. So pi times 2 squared over 4. And I'm going to minus the triangle that's created here. And that is a triangle with a base of 2 and a height of 2. So it's going to be a half times 2 times 2. And so I get pi minus 2 for that little green area there. Next up, we're going to work out this triangle. Let me shade it in different color, orange. It's a bit like the red. Okay, that's all right. Now this is 2. This is 2. We've got a few angles that we know, remember. This here was pi over 3, which means that angle is pi over 6. I've got an isosceles triangle, so that one is also pi over 6. They sum to pi over 3, which means that this angle here is 2 pi over 3. And then if I want to find out what I'm going to call it R2, it's going to be a half AB sine C. A half times 2 times 2 times sine 2 pi over 3. And that becomes, these cancel, that becomes 2 times root 3 over 2, which is root 3. It's going to like circle these as I go. So I've got R2 is root 3, got R1 is pi minus 2. So there's just one more that I have to find, actually. I know this diagram's getting a little bit messy, but if I find this sector, then I've got a whole semicircle, and I can just minus the three areas that I've just found. But actually, this sector is really easy to find because this angle is going to be pi over 3, because the two must sum to pi, the 2 pi over 3 in this angle. So now I'm finding R3. And I can just, I'm working in radians, so I just use a half r squared theta, a half times 2 squared times pi over 3. And I'm going to get 2 pi over 3. So all I need now is the semicircle, and that's area, let me call it R4. That's going to be pi r squared over 2. So I get 2 pi. And therefore the area, because technically, sorry, R is actually a region, the area of capital R is going to be our semicircle. And then I'm going to minus that little green segment, put that in a bracket. And then I'm going to minus the triangle. And then I'm going to minus that blue sector. I've got to say, I really like this approach because it doesn't require any knowledge of polar form. And you could, you could technically do this without any level knowledge. This is all GCSE, as difficult a question as it is. I mean, it's not a GCSE question really, but you can imagine it being on, say, the senior math challenge or something. And yeah, of course you could do polar form, but you could do it this way as well. So then I'm going to get 2 pi minus pi, which is pi. I'm going to minus 2 pi over 3. I'm going to get pi over 3. I'm going to end up adding 2, and I'm going to minus root 3. And I've got it in a slightly different order, but that is exactly the same as when we used our polar form. So two approaches. Yeah, good question. Well done.